So I think it's time. So let's get started. We had one example problem we didn't finish in the last class, so let's finish this problem first. Because this one is like more complicated than the previous two example problem I did in the last class. That's why I didn't want to just like post a solution and ask you guys just to read it, because it's not like similar question, but it's a higher level question. So let's see this one. So for this assembly support beam, it has a concentrated force applied at this point, and determine the deflection of the beam. So in the previous two example problem, if we have concentrated force and everything, we can pretty much use one section, and mx bending moment is function x, and one equation is good enough to represent the whole beam. And so we use one, integrate once into get the theta, integrate twice, get the y at the function of x, and then we apply boundary conditions. We can solve everything. But for this one, we know that from what you learned from the statics, if you want the expression of this beam, the bending moment of this beam as function of x, we need to separate this into two parts, either left part of the force applied or right part of the force applied. And then we need to write the bending moment equation as function of x separately, right? So for this one, first reaction force. So can anybody tell me what the reaction force here at A and at C? So this should be 2p and 3, a third of p and 2/3. Well, you can use the free body diagram equilibrium equation of the whole beam to calculate, but here to save some time, and also I can explain to you. So force in the y direction, p downward, these two together, p upward. And now let's say this is a force equilibrium in the y direction, and also the moment equilibrium. Let's take the moment about point C. Then this force will generate PA bending moment, right? Counterclockwise. So this is the force P generated moment about point C. And for the force reaction force at point A is a third of P times 3A. So it generates a bending moment clockwise PA. So moment is also in equilibrium. So if the force in the y direction is in equilibrium and the moment is in equilibrium, so we can say these are correct, right? Of course, if you are not sure during the exam, calculate it. So I mean, using the free body diagram and equilibrium equation to calculate. Don't just like you feel like you know what it is and then you got it wrong. I think a very obvious example was in the quiz 6, I think. I said if the situation is simple enough, you can skip the calculated reaction force. So they said this is P. I think I put as 1000. And for the shear, I read all of your submission, and what is the shear force? What is the maximum shear force and maximum bending moment in this beam? So I saw a lot of students wrote there directly. So this is 2 meter on right side and left side. The total length 4 meter, force applied at the middle. And then I saw a lot of students wrote directly. The maximum bending moment is 1000 times 2 meter. And maximum shear force is 1000. So, I mean, if you are pretty confident about what you're doing here, you can skip steps. But if you're not, you need to follow the standard procedure: free body diagram, equilibrium equation, shear force diagram, bending moment diagram, to find out what is the actual maximum bending moment and maximum shear force. You cannot just, oh, I feel this is correct, and then you write it directly, and all the following steps are wrong. Of course, we don't propagate error, but as an engineer, again, we want to do every step in a very scientific way. We don't do things by feeling. We're not artists. So the reaction force is 500, 500. So it should be 500 times 2 and 500. A lot of students make mistake here. So this is what I want to say. Only it's fine if you want to skip the reaction force calculation procedure here, but you need to make sure that you did it in the correct way. It's okay. You realize that you made a mistake in the quiz or in the homework, and then you'll be good in the exam. So it's like expose all the mistake before the exam. So now let's back to this equation, to this problem. So we are done with the reaction force, and as I said, we need to separate this one into two parts. First, if let's say if this is the x axis from left to right, then the first section should be when x greater than 0 and smaller than this point. Sorry, this point, right, 2a. So in this part, we imagine that we cut through a random point in this AB section. So, of course, the distance, then this distance is x. And on the cutting surface, we have the internal shear force, V, bending moment, M. And because this is the first section we consider, and cutting through this section in the second section, we put a label as the second section. So I put the subscript V1, M1 here. And reaction force, P/3. So what is the expression of bending moment M1? P/3 times x, right? Because, well, it's 3p times x generate a clockwise rotation, and M1 generate a counterclockwise rotation about the point, the point that we cut through the thing, about this cutting point. So M1x equal to P/3 times x. And so if we know this, the bending moment as a function of x, of course, then based on the equation we learned in the last class, we have the d, let's say it's y1, the x squared, not squared, second derivative, P/3x. So we integrate once, we get d ei dy dx, first derivative, plus c1. Integrate again. This is the deflection curve. We have the P18 x cubed C1x C2. C1, C2, they are unknown coefficient. We need to solve later by applying boundary condition. So this is for the left part. And now let's check the right part. So if we cut through a random point in this section, then we can do a free body diagram like this. So now x is greater than 2a and small, the total length 3a. So it means x is in this region. And similarly, we have, let's put a V2 here at the cutting surface, internal bending moment and internal shear force. And same thing here, this is P over 3, and this distance is x. So for the equilibrium equation, again, we take bending moment, we write moment equilibrium equation about the moment about the cutting point. So the reaction force at point A generated clockwise. So P over 3 times x, this is the moment. And the applied force here will generate a counterclockwise rotation. What is the moment arm for this force about the cutting rotation about the cutting point? What is the moment arm? Yes, x minus 2a. Thank you. And m2 counterclockwise equal to 0. So now we have the bending moment equation as function of x is 2p over 3x plus 2pa. So we do the same thing as here. Bending moment is equal to EI deflection second derivative. So 3x plus 2pa. So integrate once, we get the equation for the slope or theta dy to dx equal to 2 cancel out, x squared 2pax plus. Since we have C1, C2 in the first equation, now this unknown coefficient we put as C3, and EIY, the deflection as a function of x is 9px cubed pax squared C3x C4. So now we have this expression deflection at function x when x is in the left part of the concentrated force, and this is the expression if the cutting point is at the right part of the concentrated force. So this is like the y as function of x of the whole beam. So of course, the next step is apply boundary condition to solve for the unknown coefficient. And now we see that, okay, we have 4 unknown coefficients. And it's obvious that we need 4 equations to solve that 4 unknowns, right? So what are the 4 boundary conditions we can use? Anybody? we need the full boundary condition to have 4 equations and then solve for unknowns, C1, C2, C3, C4. So what are the 4 boundary conditions? Yes, these are 2. So when at A, x equal to 0, y equal to 0, and at C, x equal to 3a, y equal to 0. So these are 2 equations, but we have 4 unknowns. We need 2 more. What are the actual equations that we can use boundary condition? So for this one, that's why I say this is like more advanced level of the deflection calculation. Why? No. So whenever if we want to use the y prime at 0 equal to 0 and y prime at the point C equal to 0, that means the rotation at that point is 0. So when the rotation is 0, the boundary condition should look like this, right? Only if I put a boundary condition like this, it constrains the rotation, then we can say, okay, the y prime at A and C equal to 0. But for our current boundary condition, it's free to rotate. This is a pin joint at A and C. It only constrains the displacement, but it does not constrain the rotation. It's free to rotate. So we cannot say y prime at A and y prime at C equal to 0. Is this clear? Y prime and 2A equal to 0. You are getting close. So let's say, no. If the deformation curve is something like, I don't know how to draw it. So it's like a smooth curve. And somehow what do you mean is that the slope here is 0. But now you can use your feeling as a structural engineer. If for this kind of beam, if I apply a force here, does it make, if you have question, you can ask, but if you don't have question, please mute the mic. So when the force is applied at the middle point, how can we make sure that here the slope is 0? No, right? So if you imagine that you have force applied to the left, to the right, sorry, to the right, and then the beam probably will curve in this way. Well, it's not like symmetric, the theta equal to 0 at the middle point, but it's somewhere between the middle point and P. It's okay, don't worry. So what is the extra 2 boundary condition? I think in one class I said that if the geometry is symmetric, boundary condition symmetric, loading condition is at the middle point, of course, we know the deformation curve is also symmetric. So it's obvious that where the force applied, also the middle point of beam, it has the slope here is 0. But for this one, we know that the slope is 0, is located somewhere between the middle point and B. I didn't draw it in the exact way because I don't know how to do that. But we know that the slope at P applied at point B is not 0. So what are the extra 2 boundary conditions we can use? So even though the slope at the point B is not zero after deformation, but because we use two different equations for the deflection, one is derived from the left part, one derived from the right part. So what we can do is that, okay, at this point, we know that there's only one deflection, y here, right? And we have equation derived from the left part. We have one equation derived from the right part. So what we can do that from the two equation at point B, we have the deflection derived from the AB section should be equal to deflection we derived from the right section, from the BC section. And same thing, we know that when we apply a force and it's a beam bending, the deformation is a smooth curve. So it means that at any point, the rotation, the angle, the slope there should be the same. So if we use the equation derived from the AB section and equation we derived from the BC section for the slope, they should be the same at point B because the deformation curve is a smooth curve. The slope should be the same, the deflection should be the same. So these are the extra two boundary conditions. Now we have four equations. We have four unknowns. We can solve for this C1, C2, C3, C4, and then we solve the whole problem. So let's see how to do this. So boundary condition, first, at point A, we have x equal to 0, y equal to 0, and we know that we need to use, let's rotate. We need to use this one, right? Because A is here, so we use this equation, and we plug in x equal to 0, it means that C2 equal to 0, right? And at point C, x equal to 3a, y equal to 0. Now we need to plug in x equal to 3a into this equation and set this equation equal to 0. So can write this one as 3a cube pa 3a square c3 3a c4 equal to 0. So this is the second boundary condition. We can simplify this equation later, but let's put it here to save some time. So at B, as I said, when x equal to 2a, y1 equal to y2, which means that, okay, at the point B, if I use this equation, we derived from the left part of the point B, and we plug in 2a, it should be the same as if I use this equation, which is derived from the right part of point B, and I plug in x equal to 2a, these two, y1, y2 should be the same, right? So for this one, I can write it as 18 2a cube c1 times 2a. We already know c2 equal to 0, so that term is gone. And from the right side, 2a cube pa 2a square c3. Don't have enough space. 2a plus C4. Now this is the third boundary condition. And the last one, when x equal to 2a, same at point B, x equal to 2a, the slope at that point, at point B, should be the same if we use the equation from the both part. So basically, I need to put x equal to a into this equation and into this equation, and they should be equal. So (2a squared plus C1) 2a squared 2pa times 2a plus C3. Now we have 4 equations. This is the first one from the first boundary condition, second one, third one, the fourth. I will not show you how to calculate C1, C2, C3, C4 in detail in class because that takes a lot of time, but it's absolutely doable. We have 4 equations, 4 unknowns, and especially when C2 equal to 0 directly. So it's actually 3 equations and 3 unknowns. So I will give you the final answer directly. C1 is equal to 49pa squared, C2 equal to 0, C3 22.9pa squared, C4 equal to pa cubed. So since we have the C1, 2, 3, 4, the 4 unknown coefficients are solved, then, well, we can say this whole problem is solved, right? We have the deflection curve, we have the rotation curve. Well, the question asks, determine the maximum deflection of the beam. Okay, so now is the time we need to define. We need to find out where is actual point that the deflection is maximum. So as I explained at the beginning, it should be somewhere between the middle point and B. We don't know. So how to find this maximum deflection point? Anybody? Yes, thank you.
Could you explain why though? Why it's between B and the middle point?
You can kind of imagine that. Okay, so let's do it like this. Let's say this is the beam, and the boundary condition, if I put symmetric on both sides, and I apply a force at the middle point, then we know that the maximum deflection is at the middle point, right? There's no question for that. But
yeah,
then
thank you.
When I move this point to the right, but the maximum deflection point does not move in the same way as I apply force P. So if you imagine that I apply force somewhere here, then the curve will somehow look like this. Well, it's a smooth curve. I don't know how to draw it, but it's a smooth curve. So the maximum deflection point will also move to the right, but not move in the same distance as P. So the maximum deflection point or the rotation equal to 0 point is the same thing. It should be between the middle point and B. So yes, mathematically, the maximum deflection point, we just need to find a dy over dx equal to 0. So you're welcome. So now let's say we know that the maximum deflection point is between 0 and 2a. So we need to use this equation. Sorry, we can use this. It's here directly, right? We already derived dy over dx in this part. So we can set this one equal to 0. And then the corresponding x is where the slope is equal to 0 and deflection is maximum. So EI dy dx P6 x squared 4 9 PA squared equal to 0. So x equal to 1.633a. And for the maximum deflection, of course, we plug in x equal to 1.633a into this equation, right? So the maximum deflection, y max, equal to times 1.633a cubed PA squared times 1.638. So the maximum deflection is negative 0.484 PA. So the negative sign in front is basically mean that, well, if we normally define this is x direction, this is y direction, and negative value is deflection downward. So there's a negative sign in front. No, you cannot set in the other equation equal to 0 because we already know that the I need to remove upward. I can write it later. Because we already know that the maximum deflection point is somewhere between the point D and point B. So we know that we can only use this one in the equation we derived from the left part. We know that for all the curve in this for any point from BC, the slope is always greater than 0. It's impossible you can find a slope equal to 0 here. So you cannot. PA in the Y max. Let me check. Wait a second. Y max. PA. Yes, it's the PA square. So you mean here, right? It's PA square. Yes, you're welcome. Any question here? I think the calculation part, if there is another P, how do you know? Let's say if we have a P here, then let me answer your question first. So let's imagine that we have another P. Let's put it here. This is a random point between A and B. And for this situation, what you need to do is that you need to separate into 3 sections. First section, second section, third section. Now you have 3 sections. And if we have a force applied in this way, we can kind of expect that, okay, sorry, I really don't know how to draw this one. It should between the second section, and then you use the equation derived in the second section to find the maximum deflection. Of course, if you want to really do it in a very strict way, of course, you can try to set this one equal to the slope in this section equal to 0, in this section equal to 0, in this section equal to 0, and you solve for the x. But then you will find that in the first section, you set equal to 0, and you solve for x. X in the end is not within these 2 points. And same thing, if you set this equation, the theta, the dy dx equal to 0, you will find that when you solve for x, the answer will not be between 2a and 3a. And you know that your assumption is wrong. So you can't do it in a strict way, but you can save some time by like, okay, if I apply let's say for the original problem, we know it's between the middle point and this p. If we have 2 force, we should expect that it is between these 2 force. Yes, we need 3 parts, yes. Any other question? So I think for this one, well, it looks like a very long procedure and it's like very complicated, but let's say this part and this part, well, the moment expression, these are completely from statics. So you should be very familiar with this part. And integrate once, integrate twice is pure math, right? So this is the first 2 parts. And then apply boundary condition is basically, well, you find the boundary condition based on the boundary condition and NC, and also where the force applied, it should be a continuous deflection curve. So y calculated from the left side and right side should be 0. Rotation or slope from the left side and right side should be, not 0, it should be the same. Calculated from the right side and left side should be the same, and also slope calculated from the left side and right side should be the same. So these are the 4 boundary conditions, and we solve for the 4, we use this 4 boundary condition to have 4 equations and solve for the 4 unknowns. And so I think the most complicated part of this problem is the calculation part. Use the 4 equation, calculate C1, C2, C3, C4. It is doable, but it takes some time. And once we have the C1, C2, C3, C4, to find the maximum deflection, you set this one equal to, this one equal to 0, and you solve the point, and then you plug into the y equation that is the maximum deflection point, maximum deflection. So how to make this type of problem doable during the exam? That's the most interesting thing, probably interesting part for you guys. So with the time limitation in the exam, you probably need to do this part. There's no complicated thing here. The integration once, twice, they are pretty easy. Apply boundary condition, you need to have this equation. Of course, you need to have the correct boundary condition. You have this one, this one, this one, this one, they're correct. And you plug in, you have this equation, this 4 equation. So during the exam, what you can skip is the calculation of the 4 unknowns. Is this clear? So if I have a complicated, if there's a complicated question, similar like this, you need to divide into separate section, and then you have like 2 different equations for the bending moment, and then you have 4 unknowns, and you have 4 boundary conditions in the end. You need to solve the 4 unknowns. So during the exam, you need to do everything above here. You can skip calculation of C1, C2, C3, C4. This one takes a lot of time. It's doable, but it takes a lot of time. So this is how we deal with this type of question during the exam. Any question here? So if this part is clear, let's move on to the new topic. So this is the chapter 9, section 2, statically indeterminate means. So how will we solve the question? Well, in that situation, I will not ask this part. Well, I will post the previous exam later. You will see. Yeah. So I think in that exam, I said you only to in the end put everything until here, and you do not solve C1, C2, C3, C4. And of course, I will not ask you to find out what is X, what is, because if you don't have C1, C2, C3, C4, there's no way you can calculate where is maximum deflection located and what is maximum deflection. So I will post the previous exam later, so you will see. So in the previous chapter, when we talk about the tension compression, we talk about the static indeterminate system. When we talk about the torsion, we also talk about static indeterminate system. And of course, for bending, we still need to talk about this part. So static indeterminate, same thing. It means that purely from statics, we cannot solve this problem. Because let's say for the structure here, if we don't have this roller support at point A, this is a statically determinate means, because, okay, if there's no roller support here, we have the internal shear force, we have the reaction shear force and reaction bending moment applied from the wall to the beam, and we can have two equations, force equilibrium in the y direction and the bending moment equilibrium equation. We can solve for the reaction shear force and reaction bending moment, and this problem is done. But now we have the redundant support at point A. Now we have three unknowns. We have these two, and for this rotor support, we have reaction force here. Rotor support does not reaction bending moment, so we are already clear about that. So now we have three unknowns, but we still have two equations from statics, right? So now this becomes a statically indeterminate means because of the redundant support. So if you remember in the previous chapter, when we solved the static indeterminate system for bars, for torsion, for tension compression, we always put the deformation equation there. So that deformation equation can provide an extra equation to solve the extra unknown. So for the problem here is the same. So the extra equation we can have is the based on the deflection. So for this problem, for example, if we apply a rotor support here, it is a extra boundary, it's a extra rotor support, but it also constrains the deflection at point A equal to 0. So we can use, let's say if X is in this direction, we can use X equal to 0, Y equal to 0, right? So this becomes a extra equation, and we can solve for reaction force at A and a reaction force and reaction moment at B, then the whole problem is solved. Then the basic procedure is same. It just previously we did tension, compression, torsion, and now we are doing the bending. So for this one, again, we need to do the free body diagram and equilibrium equation. So let's imagine we cut through a random point. And we do the free body diagram. And we know there's a reaction force AY here, and this distance is X. and shear force, internal shear force V at the cutting surface, and internal bending moment M. So how to write this equilibrium equation? So of course, first we need to find equivalent concentrated force here, right? So what is the equivalent concentrated force applied here? I think we did this in the first class of this semester when I did a review of the statics. So let's do it quickly because we don't have enough time. So let's say the magnitude at the cutting point is W. So let's say W is here. And we can have the relation from the two triangle. So X over L equal to W over W naught. So the W is equal to X over L W naught. So this is based on similar triangle of this one and this one. So now, if we know this one, then the equivalent concentrated force is equal to half and times W, which is XLL times X. The length is L. No, it's not W, not X squared divided by 2. It should be this one. So equivalent force equivalent concentrated force is the area under this one. So it's equal to W times length X and half. Oh, yeah, it's 2L, sorry. You are correct. I thought it's 2 divided by 2 divided by 2L. Then you are correct. Now we have the equivalent concentrated force. So we can write the, let's say the cutting point is C. Then the moment equilibrium equation. Reaction force generates a clockwise, so it's negative times X. And equivalent concentrated force generates a counterclockwise, so it's positive. And the moment arm is X3 over 3. And bending moment at the internal bending moment at the cutting surface is counterclockwise. So M equal to AY X So this is the bending moment equation in terms of X, and of course, AY is unknown. And since this is a linear change distributed force, we do not need, like in the previous problem, we need to divide it into different sections. For distributed force is distributed over the entire cross section, entire beam, then one equation is enough. So now we can write this one as, because the bending moment is equal to EI dy dx second derivative equal to AYX integrate once, so it becomes the dy dx, the slope equation equal to ay um, 6 4x c1, and integrate again, ei times y equal to x cubed 120 L x to the C1x plus C2. So now this is the deflection as function of x. We have this equation now. So we know that in this equation, we have three unknowns. So we have C1, C2 from the integration, and reaction force here is unknown. So what are the three equations we can use? We need three boundary conditions. So I think I already talked about it. At point A, deflection equal to 0, right? That is the first one. At point B, deflection equal to 0, slope is equal to 0. So these are three boundary conditions we can use. So x equal to 0, y equal to 0. So C2 equal to 0. At point B, the total length is L, so x equal to L. Y equal to 0. So we plug in x equal to L into this equation. Ay over 6L cubed 120. This L is gone. L to the fourth. C1L plus C2 equal to 0. And at x equal to L at point B, the rotation or the slope there is also equal to 0. It does not allow to rotate. So L squared 24 L cubed C1 equal to 0. So basically you plug in x equal to L into this equation and it's equal to 0. And now we have the three unknowns, and we solve, of course, C2 is already solved here. So AY is equal to C1 So the question asks to derive the equation of elastic curve. Of course, when we have C1, C2, and AY, we have the elastic curve. And the second question is the first one is determine the reaction at point A. This is the reaction at point A. And the question A, B, we already solved. And the C, we need to determine slope at point A. So of course we plug in x equal to 0 into the slope equation. Let me write the, so this is for answer A. For B, y is equal to 120 EIL 2L squared X cubed. So this is a deflection curve. And part C asks at point A, X equal to 0, and we need to find out the dy, the slope there. Where is the equation? So it's this equation. When x equal to 0, this one is gone, this one is gone. And the slope here is equal to C1 divided by EA. EI, sorry, EI, not EA. Any question here? So the basic idea is the same. We just have the bending moment equation and derived once we get the equation of the slope and derive and integrate again, you get the equation for the deflection, and then we apply boundary condition and we solve for all the unknowns. So basic idea is the same. Probably the calculation part is a little bit complicated, but it's definitely doable. Any question here? So if no question, let's move on to the superposition method. It's a new topic again. But the basic idea is very easy. It's just calculation. It's complicated. So we know that for this superposition method, it's just a different way to calculate this type of problem. It is okay that if you don't know the superposition method, you can use this method to calculate everything. So it is fine. But some of you may feel that superposition method is a relatively easier way to solve this type of problem. So for example, if we use the regular method to solve this problem, we need to divide this one into two sections. This is the first section, this is the second section, and we need to have the bending moment equation in the AB section, and we integrate once, integrate twice, and we have the two equation, slope equation and deflection equation for AB section. And in the BC section, we write the bending moment equation and integrate once, we get a slope equation. We integrate twice, we get the deflection equation. And then we apply boundary condition. So boundary condition, again, here is at point C, deflection is 0, theta is equal to 0. These are two equations. At point B, because it's a smooth deflection curve, we know that if we use the equation derived from left part and the right part, it should be the same. So at point B, y1 equal to y2, theta 1 equal to theta 2. So it's same as it's almost the same as this problem, right? So we can use this method to solve this problem. But if we want to find a method and extra method that make the calculation part easier, what we can do that we separate this one into two. So we separate these two loading conditions. One is force. We calculate everything based on if only force applied, and we calculate this based on if only bending moment applied. And then in the end, we add the deflection and slope of caused by two loading conditions together. And then that is the deflection and slope of the force combined. So that's why it's called superposition. So we separate the force, we add them together in the end. So for this one, let's say, so this loading condition, we can put it as if only bending moment applied, or, and sorry, if only concentrated force applied. And we calculate separately. So let's say this is one, loading condition 1 and loading condition 2. So for the first one, it's a pure bending problem, right? So bending moment is constant through the whole beam, is equal to PA. So this one is easy. So this is equal to EI dy dx second derivative. So integrate once, we can have EI dy dx PAX plus C1. And integrate again, we have deflection PA x squared C1x plus C2. So we can apply boundary condition for this one. We know that, well, for this problem, it's much easier if you set the x is from right to left, because if you put the x-axis in this way, for the boundary condition, on this side, you can simply put x equal to 0, right? So here, x is 0, x equals 0. So we can make the calculation much easier by setting the x-axis from right to left. So the first one, from the first equation, x equal to 0, dy dx equal to 0. So C1 equal to 0. And also at point C, the deflection equal to 0. So from the second equation, x equal to 0, y equal to 0. So C2 equal to 0. So the first part is super easy. Imagine that if you put the x in this direction, then it's x equal to L equal to 0. And x equal to L, y equal to 0. The calculation part will be easier. So don't torture yourself during the exam. So now y, I can write it as 2EI theta is equal to PA EI times x. So because the question asks the slope and deflection at a free end, so in this way, we just plug in at point A, y A1 PAL squared 2EI theta PA EI L. So this is purely from the first loading condition if we only have the bending moment PA applied to the beam. So this is the deflection at the free end, and this is the rotation at the free end. So we are done with the first part. So the second one is if we only have the concentrated force P applied on the beam, what is the deflection and the slope at point A? And then we add these two together. So this one is a little bit more complicated because, well, it's similar as this one. I would say for this problem, it does not make things easier because you still need to separate. Well, we consider it's an alternative method, something we need to know, but I don't think it makes things easier. So for the second loading condition, when x is between 0 to A, which means it's the left part of the force applied, left part of the P, of the point B, then let's do the right part because we're setting the x-axis is from here. Now we have the P here. P reaction force, reaction shear force, reaction bending moment. And on the cutting surface, we have the internal shear force and internal bending moment. But of course, internal shear force doesn't matter, doesn't change anything. I just put it here for completeness. And the bending moment equilibrium equation, I can write as about point D, the cutting point is P x minus A. And, oh no. So this one is equal to EI dy dx second derivative, and integrate once we get the dy dx. EIy is equal to P over 6x cubed C1x plus C2. So this is the bending moment equation for the right part of the force applied, and we have the integrate once, integrate twice, we have the slope equation and the deflection equation. And we can apply boundary condition here. So boundary condition, I can write it at C, when x equal to 0, y equal to 0, so C2 equal to 0, and x equal to 0, the rotation is equal to 0, so C1 equal to 0. So for this one, theta dy dx equal to P over EI half x squared minus AX. And the equation for deflection, x cubed over 6 AX squared over 2. So now we have these two equation for rotation and deflection. And we know that for calculating the deflection and rotation at point A, we can calculate deflection rotation at point B first, right? So we plug in x equal to A into these two equations. So for these two expressions, if we plug in at point B, x equal to A, then theta B caused by loading case 2 is equal to, well, you plug in, I just put the final answer here directly, 2EI Y B2. Sorry, x equal to A not equal to 0, x equal to, at point B, x equal to A, 2EI. Y is x minus A, x minus A. Where do we have x minus A? Oh, you mean here? Oh, okay, sorry. I guess because I feel time is limited, so I skipped the first the step. So I think I still need to put it here. So bending moment clockwise, we put negative minus PA clockwise plus Px equal to 0. So from this equation, moment equilibrium equation, we get Px minus A. No, it's Px minus A. Do you have a question about this equation or not? This one, and this one. Yeah, you're welcome. Sometimes I try to skip some steps to save some time, but I don't think it's a good idea. Thank you for your question. I probably need 2 more minutes, but let's see. So actually, when I calculate here now, I feel that it probably saves some time because we do not need to calculate for this one. We don't need to calculate bending moment and in this section and calculate and integrate once, integrate twice, and have the deflection and stuff and everything, because now this one, it does not deform, right? This, if you apply a force here, and deformation is generated everything to the right of P. And for the so this is the deformation generated by the P to the right part. And for this part, it would maintain a straight beam. So whatever slope is at P, apply, so this is point B. This is point B, so this is point B. Whatever on the left side of the B, it is a straight line. It's not a curve. So for this loading condition, we already calculated everything here, right? At point B, the slope and deflection. So for this one, we just need to use a triangle. Let's use different color. Because this part, we maintain a straight beam. There's no force applied, it's free of force. We know this angle, or we say this angle is the same as the slope at point B. And we can solve. This is L minus A, right? We know this angle, this is equal to the slope at point B. We already calculated. So this part is extra deflection in this section. So we can use the sine the rotation equal to this distance over this distance. We can calculate the y deflection. So, or we use tangent because it's more deflection, it's more deformation, so it doesn't matter. I probably need extra 2 or 3 minutes. Sorry about that. If you need to leave, you can leave now. So tang theta equal to y AB section of equal to theta. So y AB equal to L minus a theta B2. So it's P A square 2EI A minus L. So y A2 is equal to y B2, whatever deflection at point B plus the deflection at AB section, which is a straight line. So this one is equal to PA cube 6EI PA square 2EI. So in the end, as I said, superposition is basically we calculate deflection slope at the point A here and deflection slope at point A here. We add 2 of them together. So the total deflection is y deflection from the first loading condition at point A plus the deflection from the second loading condition at point A. So it's equal to PAL squared 2EI. Plus PA cube 6EI. PA squared 2EI. Rotation, same thing, we add them together. Rotation caused by first loading condition at point A and rotation caused by the second loading condition at point A. So it's PAL over EI minus PA squared 2EI. I'm done. Sorry for running over time again. Any question? So I think in the homework I said you do not need to use the appendix. So in the appendix it gives like what is the deflection caused by each single loading condition and put in the table and give you the final answer. I do not recommend that you use that in our class because our class is to build a solid foundation. You need to know how to calculate yourself. So for the homework, you need to use this method. And for the second problem, I will post a complete solution. So thank you for coming to class and have a great weekend. Thank you.